Hi everyone, welcome to Unit 3 of our BERD Academy course Understanding Uncertainty in Data-Driven Research, or How Uncertainty Shapes Machine Learning. Today we're going to look at different types of uncertainty and the sources of uncertainty. We will differentiate between aleatoric and epistemic uncertainty and see where it arises throughout the machine learning pipeline. Okay. Let's go. There are commonly in machine learning you differentiate between two different types of uncertainty. One is called aleatoric uncertainty. It comes from the Latin term alea, meaning game of dice or gambling. And as the name already tells you, it has something to do with like the inherent randomness of outcomes. Just like gambling, you don't really know the outcome when rolling dice, for example. And oftentimes it is said that it is irreducible because it's just the inherent randomness. You cannot do anything about the inherent randomness of any kind of process. And that's why you cannot reduce it. Epistemic uncertainty comes from the Greek word episteme, meaning knowledge. And it relates to the lack of knowledge about our models, about processes, about the data. And since it relates to the lack of knowledge, if you had the knowledge, you were less uncertain. That's why it's said to be reducible in principle. Oftentimes it makes sense to differentiate between irreducible and reducible uncertainty, because it would help you guide your next steps. If you know you have a lot of aleatoric uncertainty and maybe the process you want to describe is just too random to describe, maybe that already helps you. However, if you know it's reducible in principle, you could collect more data, build a better model, or change anything about your setup to reduce this lack of knowledge. So that's why I think that those two terms and this differentiation came up in the first place, because it really helps you guide the decisions. Maybe some more visualizations to this. Imagine we have like this classical regression type example. We have some curve where the data follows exactly this curve. Here we might have not observed any kind of data, so we have no idea, does the curve look like this? Maybe I can even put like does the shape look like this, for example? Is it just a straight line? Is it maybe something like that? We just don't know. We have no idea about the uncertainty or the shape of the curve here. So we have a lot of epistemic uncertainty. However, here we can see that the points just have quite some variation in them. And we have a lot of aleatoric uncertainty in this area because they do not follow the line very perfectly. So we have a lot of the remaining variance here. Okay, so common assumptions that we have about those kinds of uncertainties, wait, let me change to laser pointer again, is that the aleatoric uncertainty is the data uncertainty because it comes from the data and it is irreducible. Epistemic uncertainty is the model uncertainty and thus it is reducible. And also that if you increase your training data, you can reduce your epistemic uncertainty, as commonly stated in, for example, those two papers, one by Eike Hüllermeier and Willem Wageman, Aleatoric and Epistemic Uncertainty in Machine Learning, an Introduction to Concepts and Methods. I very much recommend this paper. It really explains this aleatoric epistemic concept very well and introduces many methods how to quantify them. However, I still argue that this definition is a little bit too simplistic, because the definitions of types are usually not consistently defined. You often find in literature just something like aleatoric irreducible or aleatoric data uncertainty, epistemic model uncertainty, but you rarely have very precise mathematical definitions of those terms. You oftentimes only have mathematical definitions of how it is supposed to be measured, but also there is much to discuss there. Additionally, the causes of uncertainty are not related to the types of uncertainty. So the sources are also not related to the types, which leads to the fact that basically if you just measure aleatoric and epistemic but don't really know where they're coming from exactly, you also don't really know how to reduce the uncertainty or don't reduce the uncertainty. Okay, and that's why we will go over some examples and see how we can maybe question some of those assumptions. Also, if you can see, if you just say aleatoric is the data uncertainty and epistemic is the model uncertainty, we do have a very close connection between data and the model. I mean, usually the process of machine learning is that given the data, you decide what kind of model to do, and separating those different types of uncertainty by just saying, well, one comes from the data and one comes from the model is also already too simplistic. In the next videos, we will look at the sources of uncertainty. Namely, we will look at omitted variables, which can be missing features. Imagine, for example, we have a satellite image and we could additionally have like other sensors like LiDAR or radar that could give us more information about whatever we want to measure. We can have errors in X, so errors in our data. We can have imperfect observations for various kind of reasons. Maybe the quality of our images is not good enough, or you can also think about text examples or anything else. In Unit 2, we discussed labels a lot, so you already know that there might be incorrect labels, the reasons for them, or also the fact that we have proper variation in the labels. Also, oftentimes the goal of machine learning is to actually apply those models in real life, to have a deployment of the models that were trained before. I mean, yes, we all are from research, so oftentimes research is also just interesting to figure out how machine learning works, for example. But as soon as you're more applied, you really want to apply those models. I'm sorry. We can observe changing processes. So, for example, you train a medical model on data from people from one hospital in one country, and then you want to apply that in, for example, a completely different setting. And you might have changing processes because, for example, the kind of people that actually can seek medical help in a hospital is different depending on, for example, how health insurance works in that country or not. Or also the types of sicknesses might be different in different parts of the world. And so it's important to really figure out where can the uncertainty come in all the different steps. Okay, and we will go through those examples in the next video. We are funded by the Deutsche Forschungsgemeinschaft, and this is the copyright.